This conference will now be recorded.
So today we'll start with problem and two important reactions for haloalkane, that is substitution and elimination, both we have completed, and two more types are left. But before that we'll discuss this problem, and after finishing discussing this problem and the two more reactions for haloalkanes, next topic will be the reactions that are observed for haloarenes, that is aromatic ring halogen attached to it. So in this problem, it is saying that CH3, CH2, CH2Br, which is basically haloalkane. And it is treated with Z. Now Z is CH3, CH2 minus, and Z may be another base also, which is Me3CO minus. So Z may be A or Z may be B. Two types of reagents are there. And two types of reactions also we are getting. So when we are using Z with CH3, CH2, CH2Br, we are getting substitution reaction. This is the corresponding rate constant. As it is substitution, so there is notation Ks. The product is Br simply replaced by Z. So obviously this is substitution. Br is removed as leaving group. But there is another possibility, which is elimination. And now the rate constant, the term we are using Ke. So in this case, this Br will be removed, and also hydrogen from the middle carbon, that will also be removed, and you are getting the elimination product, which is containing CC double bond. So here net removal of H and Br is occurring. So two types of reactions are possible, and Z may be also A or it may be B. So Ks and Ke, these are the rate constant for the substitution and elimination reactions respectively, and the ratio of these two rate constant, in the denominator we have Ke, numerator we have Ks. So this ratio is denoted by mu. So based on all this information, now we have some options, and in the options 1, 2, 3, 4, it is saying that mu B is greater than mu A. That means when it is mu B, then the reagent you are using is Z equal to B. And under this condition, that is when the base is Z is tertiary butoxide, under this condition, this is this ratio will be denoted as mu B, and when it is A, it is mu A. Now mu B, it may be greater than mu A. This is one possibility that you can also find in option 3. So 1 and 3, these two parts are same, but in option 2 and 4, now mu A may be greater than mu B. So we have to find which one is correct. So 2 and 4 same, and 1 and 3 same. There is another part also in each options. It is saying that for elimination reaction, see, it is Ke for both. So Ke, that is elimination reaction, when you are using the base ethoxide A and when you are using the base B. So two different elimination reactions are there depending on different reagents we are using. So it may be that KEA is greater than KEB or the reverse one. So KEA greater than KEB, that we can also find in the last option, but these two options are same. Okay. Now when it is the fact that Z is equal to A, that means now it is ethoxide base. Now under this condition, we know that when the base is very simple, it is not very hindered, and it is not also very strong compared to B. Obviously tertiary butoxide, it is not only hindered, it is also very strong base, but compared to B, A is not so strong, and also it is very simple. So under this condition, obviously substitution product will be high compared to elimination. That means when Z is equal to A, Ks will be greater than Ke. Okay, and when Z is equal to B, that means now the base is very hindered. Under this condition, elimination reaction will be favored. So now Ks is not so high compared to Ke. Fine. So obviously now as Ks is not so high, now Ke is high. even if it is not exactly high, then also that is, if, as we do not know what is the exact value of Ks and Ke, we can maximum have some probability that it is compared to Ke high. Now obviously, even if it is not true, that is exactly if it is not high, then also we can say that when you are using very simple base, substitution reaction is favored, here elimination is favored. So that is why this ratio, that is mu A and mu B. So when it is mu A, basically mu A is equal to Ks by Ke for A. Fine. And similarly, mu B will be equal to, this is also same ratio, but now the substitution reaction that you are getting for the base B and Ke, that is also for base B. So obviously mu A, that will always be high compared to mu B. Okay, because when you are using the base B, now the chance of getting elimination product is high. So compared to numerator, now denominator will be high. So that is why mu A will be greater than mu B. And that you can find in option 2, and you can find also in option 4. So now when we know that any one of 2 and 4 will be correct, next thing that we have to check that for elimination, now there is nothing about substitution. Now for elimination, compared to the base B, when you are using base A, in which case elimination reaction high. But see, as the structure B, it is very hindered base, and for hindered base we know elimination is always favored, right? So elimination reaction, that is rate constant for elimination, when you are using B, that will always be high than the rate constant for elimination when you are using B. That means KEB, that will be greater than KEA. And that you can find in which option? It is in option 2. So here are the points that you have to keep in mind. Among the given bases A and B, tertiary butoxide. Tertiary butoxide means this one, B. It is very bulky, so obviously it will favor elimination. And the other base, which is ethoxide, this is A, it will favor substitution. So when Z is equal to CH3CH2O minus, that means it is A, substitution favored. And when Z is equal to this one, that means B, then elimination favored. So that is why these conditions are correct, and that you can find in option. So option 2 will be the correct option. Okay. Next problem. Now see, this is integer type of problem. So there will be a simple number. 1,2-dibromopropane. That means propane, 3 carbon chain, but at 1 and 2 position, that is the first carbon and the middle carbon, there will be 2 bromine substituents. And you are treating this molecule with X moles of sodium amide. Now sodium amide, NaNH2, this is a very strong base. And here the base is basically the ion amide, NH2 minus. So you are treating it with X moles of NaNH2 followed by treatment with ethyl bromide. That means you are not only treating it with X moles of NaNH2, but after that you are also treating it with ETBr. It gave pentine. Okay, pentine means it is 5 carbon chain, but as it is ine, that means triple bond will be there. Though we do not know what is the position of triple bond, but that is not important. The important thing is we are getting CC triple. You have started with 1,2-dibromopropane. So here total number of carbon is basically 3 carbon chain. And from ETBr you are getting 2 more carbon. That means total number of carbon 3 plus 2, it is 5. And this, that is why final molecule is pentine, which is containing 5 carbon. Now the structure of 1,2-dibromopropane is this one. So this is carbon number 1, this is 2, this is 3. So this is a propane chain, right? But at 1 and 2 position there are bromine substituents. Now here the role of amide, that is the role of NH2 minus ion, is to capture the beta hydrogen. Now in this molecule, removal of HBr is possible, elimination is possible because base is there. But see, 2 bromine atoms are there. So it may be that the elimination that can occur 2 times. Fine. So here what will happen? When you are using NaNH2, basically 2 moles directly written in the arrow, but you can also write it separately step by step. Here both elimination, that is elimination of two times elimination is occurring and both are written simultaneously. But you can also do it in this way. Suppose if we remove the first bromine, there is formation of double bond like this, and again another HBr can be removed. So now you are getting finally propine. So this is actually propine. So 2 moles of NaNH2 we have already used. Now this is the number 3, that is third mole of NaNH2. Now when you are using this, there will be removal of this hydrogen, that is the terminal hydrogen, and this carbon is sp hybridized, and we know that sp hybridized carbon, it is very electronegative in nature because of 50% S character, and that is why after removal of this H, you are getting this sodium salt. Sodium is coming from NaNH2, and this negative charge, it can be that is over this carbon. It is very stable because this carbon is very electronegative. So CH3 C triple bond C minus, and finally as it is written in the question that it is treated with ethyl bromide. That means ethyl bromide is this molecule. So this negative charge, that is CH3 C triple bond C minus, this is actually now behaving as nucleophile and it will attack here. And this is SN2 mechanism because this is 1 degree alkyl halide, and we know for 1 degree SN2 is favored. But whatever it is, the important point is it is substitution. Whether it is SN2, SN1, that is not important. Important thing is it is substitution. So Br is finally removed. So this carbon and this carbon, these two now it will be joined, and finally you are getting pentyne. Basically it is 2 pentyne because if you are numbering in this way, 2 position there is triple bond. But position is not important. Even without knowing the position, you can answer this question. So you have to find the value of X. So how many moles of X you have used? It is total 3. So for the first 2 moles of NaNH2 that are actually used for removal of H and Br, net removal of H and Br. And the third mole of NaNH2 that is used for removal of this H, which is terminal hydrogen. It is acidic in nature because it is attached to sp hybridized carbon. Okay, so this is number 3. And this is the question that is asked. That is, what is the value of X? X is the number of moles of NaNH2. So correct answer is 3. Next question. With excess sodium iodide, how many halogens in the given compound, which is given, the structure is already there, in the given compound can be substituted, that is substitution reaction is possible with reasonable speed. That means it is not that reaction is occurring, reaction may be there for all these halogens, but reasonable speed. That means it should not be very slow. More or less it should be high rate. And how many halogens are there in this molecule? 1, 2, 3, 4, 5 and 6. But the question is it possible that all these halogens will be replaced by substitution? And here you are using excess sodium iodide. That means I minus is the nucleophile. So all these halogens that you are seeing, they are actually behaving as alkyl halide. So here the reaction is I minus, it will attack R, X will be removed, and there will be formation of Ri, which is a substitution product. But is it possible with all these halogens? That we have to check. So out of these 6 halogens, if you notice carefully, here the Br is not directly attached to the aromatic ring. So this is not aromatic at all. This is aliphatic. And for aliphatic alkyl halide, because it is not haloarine, it is haloalkane. Substitution is obviously possible, and here substitution will take place very readily because Here, if it is undergoing through SN1 mechanism, though here simply mentioned SN, it is not clearly mentioned whether it is 1 or 2. So you can consider SN1 as well as SN2. So here positive charge is very stabilized because it is a benzyl position. So here it is possible. But fluorine, which is directly attached to aromatic ring, here for haloarene, this type of nucleophilic substitution is not possible. So nucleophilic substitution for haloarenes, it will be possible under, that is, some special cases will be there where it is possible. Though this is not very common. Mostly substitution is common for aliphatic molecules, that is alkyl halides, not for haloarene. That is aryl halide, it is not common. Though we will see some examples probably in this class or in the next class. But remember that is not very common. And why it is not common? Because here this double bond between, the bond between carbon and the halogen, it has some double bond character because of resonance, and that is why to break this bond is very difficult. So when halogen is directly attached, this type of substitution, it is not very common. So here it will not take place. Now this bromine, it is not attached to aromatic ring, but see, it is basically, if you focus on this part only, it is basically vinyl bromide because it is attached to sp2 carbon, and in this carbon also double bond character is possible between bromine and the carbon, like this. So breaking this bond is very difficult. So here also it is not possible. Then this is not possible. Next is what about this one? Now this carbon, it is 2 degree, and here it is obviously possible, no problem is there. This bromine number 2, this is also possible, but so this is not, this is also not, fine. But what about this one? Now this carbon, it is attached to 3 more carbon, it is 3 degree, but that is not the point. The point is it is bicyclic rigid type of structure. Now if you consider SN1 reaction, then positive charge will be like this. If I am drawing simply the part where rest of the part is not required, just focus on this part. Now positive charge is on this carbon, but this carbon is not planar. But what we know that sp2 carbon, it should always be planar, but it cannot attain planarity. So that is why this mechanism is not possible. Here SN1 is not possible. And if you consider SN2, then also there is problem because the nucleophile is I minus. And we know that in SN2, the nucleophile always attacks from the back side of the leaving group. But here I minus attacking from the back side, that is also highly unlikely. It is not possible. And the reason is because of this rigid bicyclic type of structure. So both SN1 and SN2, there are some problems for which substitution is not possible. So that is why this is not possible. Only possible is Br, Cl, and this Br, but not these two. So out of 6, only 3 halogens you can substitute with reasonable speed, but not the other 3. So this is also integer type of problem, and the correct option will be 3. Halogens attached to sp2 hybridized carbon cannot undergo nucleophilic substitution easily. So that you can already see in this case. So it is not possible here. Even the bridgehead halogen. Which one is bridgehead halogen? This one is bridgehead halogen. So here also substitution is not possible. If I give number here, this is 1. So this is number 1, which is bridgehead. So that is why this chlorine, because of bridgehead type of structure, and also this fluorine because it is directly attached to aromatic ring, and this bromine which is attached to sp2 carbon, in these 3 cases substitution is not possible, but the other 3 cases substitution is possible. So answer is 3. So after finishing the problems that are related to substitution and elimination, now we have reached to the topic which is the third type of reaction that is possible with haloalkanes. Total 4 types possible. Under these 4, 2 we have already finished, which is substitution and elimination. These 2 are the broad category. Now we have reached the number 3, which is reaction with metals. So here we will see how haloalkanes they can react with metals. But before that, you have to understand organometallic compound. What is organometallic compound? So as the name suggests, organometallic, that means organo this term is generated from carbon, and metallic that means metal. So it is related to carbon metal bond. So haloalkanes react with metals and it forms compound which contains carbon metal bond. And this carbon metal bond when present in any compound, that will be called organometallic compounds. So in organometallic compounds, you can find this type of bond. Here carbon and metal, if you consider their electronegativity, obviously carbon is less electropositive than metal. That means from electronegativity point of view, carbon is more electronegative. So that is why when you will consider bond polarity, negative side will be towards carbon, positive side will be towards metal. Okay, so this is because of this type of polarization. Now this carbon, it can behave as nucleophile or it can behave as base because of this charge, negative charge density. Okay, now there is a very common term, probably all of you heard, which is Grignard reagent. So Grignard reagent, that is basically one type of organometallic compound, because in Grignard reagent carbon magnesium bond is present. But before that, we will also see some other examples which are not exactly Grignard reagent, but they are examples of organometallic compounds. Here we have taken ethyl bromide and it is treated with 2 lithium. Now lithium is metal, it is from group 1 and we are using dry ether. So the solvent that we are using here, it should be dry, it should not contain any traces of water, because the molecule that you are trying to make, which is this organometallic compound. Why it is organometallic compound? Because carbon lithium bond is present, that is why it is organometallic compound. And the name is ethyl lithium. Now these molecules are very sensitive to water. Okay, if a slight amount of water is present in the solvent, then what will happen? As there is negative charge density over this carbon which is directly attached to metal, this will try to capture that hydrogen in the water molecule, which is not expected, which is not desired. As a result, ethyl lithium that will be decomposed. But that we do not want. We want to prepare this organometallic compound, and that is why solvent should be very dry in condition. Then the next example, we have again taken ethyl bromide, but now we have taken 4 moles of this molecule in presence of sodium or lead. Anyone you can take, and it is also 4. And this is actually sodium lead alloy. It is written in this way. And what will be formed here? Et4Pb, that means tetraethyl lead is formed. And this Br is now attached to sodium, so NaBr will be produced. And out of this 4 Pb, now 3 Pb, they are removed. So tetraethyl lead, in short TEL. So this is also example of organometallic compound. If you draw the structure of this, it will be like Pb attached to 4 ethyl groups. So it is tetraethyl lead. Now what about Grignard reagent? Grignard reagent is basically where carbon magnesium bond is present, and the general way by which we represent it is RMgX, because magnesium, here you have seen the use of lithium. Magnesium, it is from group 2 and it will have 2 bonds. So if one side there is R, that is the carbon part, other side there is halogen. In this case, lithium is simply attached to this R group. You can also write it as RLi because its valency is 1. It is from group 1. Fine. But for magnesium, as it is from group 2, now its valency is 2. So that is why on one side there is R, another side there is X. You can also see for lead, as it is from group 4. Here 4 valency satisfied. So that is why 4 R groups are attached. But for magnesium, there will be 2. So here the R group is basically alkyl group. It may be aryl group also, that is it may be any pH ring or substituted pH ring, and X is obviously halogen. Okay, so this is the Grignard reagent RMgX. Next we will see that why organometallic compounds are so important. Because it is important because its application is very versatile. You can see from this example, huge applications for this molecule is possible depending on what kind of other reaction partner you have used. Suppose this is the molecule R prime MgX, and how it is formed? It is formed when you treat magnesium with Rx. So suppose you have any alkyl halide Rx. Here I can write R prime because R prime is there. In presence of Mg and dry ether, there will be formation of RMgX. So in this way you can prepare Grignard reagent. So this is the reaction between haloalkane and metal. Here the example you are seeing is for with magnesium. It may be lithium or it may be sodium lead alloy. Now once this Rm prime MgX, which is Grignard reagent, it is formed. Now depending on what kind of reagent you are using. So take this example. If it is reacting with H2O, basically as I have mentioned for these two reactions, that the reaction should take place in solvent which is completely dry. There should not be any traces of water because you are synthesizing this organometallic compound. So organometallic compound, when they react with water, basically it is capturing the hydrogen of water and it is forming R prime H, and OH is also there. So magnesium, now it will be attached to X and OH. This is a byproduct. So because of this type of formation of alkane R prime H, if you are trying to, that is, if your purpose is to make R prime H, it is fine. But if you just want to make R prime MgX, then this reaction must be prevented. So that is why water should not be present in the salt. Next, if it is reacting with RCN, now RCN is basically RC triple bond N. So when it reacts with RCN, there is formation of R prime COR. So it is not single step, though it is written here as single step. So what happens? This R prime, which is basically R minus, R prime minus, it attacks this carbon. Now triple bond will be broken and there will be reaction like this. R prime is here, negative charge over nitrogen, and the other part of Rm prime MgX, that is MgX, that will be now attached. This is the first step, and next, this is not very stable structure. Next, if you are hydrolyzing it, what will happen? Now this C triple bond will be broken and there will be formation of RC double bond O R prime. So R prime COR, that will be the final product. Now this R prime, as it is mentioned here, it can be alkyl group, it may be vinyl CC double bond, it may be aryl, and the halogen maybe mostly it is Br, but Cl(I), that these two also possible. Fluorine we normally do not use. Then reaction with ketone, here product will be same type of mechanism that I have just drawn with RCN. Now the product is you are getting alcohol. Fine. So two R groups already attached to this carbonyl carbon and a new R prime is coming. So this will be 3° alcohol. If it is RCHO, that is aldehyde, this is the general structure of aldehyde. Now you are getting R prime OH R. So this is 2° alcohol. If you are treating it with formaldehyde, ACHO, then you are getting 1° alcohol. So depending on what kind of carbonyl compound you are using, you can make 1°, 2°, 3°. So this is also a very good method for preparation of alcohols, using this carbonyl compound and Grignard reagent. Next, if it is treated with ethyl ester, ACOOET, now you are getting again alcohol. And the red arrow that you are using, that is actually the preparation method for R prime MgX starting from R1. So when it is reacting with ACOOET, so this is ester, ethyl ester of formic acid. So here the reaction is like this. This R prime minus of RMgX, it will attack this carbonyl, sorry, this one. This OET will be removed. So first you will be getting ACOR prime, But this is not end of the reaction. If you are using excess of Grignard reagent, another R prime that will also attack, and now there will be OH. So finally you are getting R prime, 2 R prime attached to carbon containing OH. So this is also 2-degree alcohol. And 2 R prime, that means per molecule of HCO2 ET, you are using 2 molecules of R prime MgX. Then the next molecule, ETO COOET. So as if here you have ester group both sides. So first attack of R prime, this OET removed, second R prime, this OET will be removed, and the third R prime. Now this carbonyl, it will be converted to alcohol. So here you are getting 3-degree alcohol. If you are using RCO2ET, again you are getting see, it is the same reaction as you have observed in case of HCO2ET. Here also 2 R prime, that means per mole of RCO2ET, you are using 2 moles of R prime MgX. So this is also alcohol. Reaction with carbon dioxide, that is also possible because the structure of carbon dioxide is like this. So there is also carbonyl group present. So R prime minus, it will attack here, negative charge over oxygen, and it will be basically OMGX. And finally, what you will be getting, if you are hydrolyzing this molecule, you will be getting carboxylic acid. And if you are treating it with epoxide, we know epoxide is very strange ring because it is 3-membered. So R prime minus, it will attack this carbon oxygen bond will be broken. So R prime 2CH2 because of these 2 carbon, and then OH. So this is also 1-degree alcohol. So see how versatile is the application of Grignard reagent, which is R prime MgX, and R prime MgX is basically the product that you are getting when you are treating haloalkane with metal. So this is reaction of haloalkane with metal. The product is R prime MgX, and the product is very having very versatile application that we can see here. Reaction with metals, another example we'll see, that is different reaction, which is known as Wurtz reaction. This is an organic chemical coupling reaction where sodium metal is reacted with 2 alkyl halides in the environment provided by a solution of dry ether. And what you are forming, that is, what is the product? The product is higher alkane. Higher alkane means the alkyl halide with which you have started, if it is containing, suppose 2 carbon, arbitrarily I am saying, then after reaction, the alkane that you are getting, it will contain more than 2 carbon. So that is why we are calling it higher alkane, along with a compound containing sodium and halogen. So this is the byproduct. Now look at these structures, these reactions. Suppose this is a general expression you are seeing, the first reaction, this is a general reaction. Rx, it may be any alkyl halide. So 2 sodium and 2 Rx there. So this halogen Na and the other halogen, it will form NaX, sodium halide, and these 2 R groups that will be now attached. So this is coupling of 2 alkyl group. So carbon-carbon bond is formed, and the condition is you are using pure and dry ether. Here also solvent should be free from moisture. And see here, initially if it is suppose ETBr, then 2 ET attached. So initially it is 2 carbon, but now 2 carbon, 2 carbon, total 4 carbon. So you are getting higher alkane. So starting with you have started with haloalkane, but you are getting final product. After reaction, you are getting alkane because halogen is removed along with sodium. Now we have actual example in the second reaction. Methyl chloride, 2 sodium, again another methyl chloride. So NaCl will be removed and methyl attached, you are getting ethane. So single carbon is there, but now there are total 2 carbon. So this reaction, it is a very good way for increasing the number of carbon, right? Then the third reaction, now we have isopropyl group CH3, CHCl, CH3. If two molecules, obviously we need to take. So this carbon and the other carbon of another isopropyl chloride, that will be attached to this CC bond, that is the newly formed bond. Reaction 4. Now this is also general reaction, but here what is the difference with the first reaction? Now two different alkyl halide you have taken, one is Rx, another one is R prime X. So this is that is mixed structure will be there, and see different possibilities are there. It may be that one Rx reacting with another Rx. In that case, this will be the product. It may be one molecule is Rx, another one is R prime X. In that case, this is the product. And the third possibility is two molecules of R prime X, so R prime attached. So basically now you are getting total 3 types of molecules mixture you are getting. So for example, suppose you have taken methyl chloride, ethyl chloride and sodium. So what you will get? Methyl attached, fine. Then one methyl is attached with C2H5. That means total number of carbon will be 3, that you can see here. This is basically propane. And the third possibility, 2C2H5 will be attached. So that will be C4H10. So this is the third possibility. So see, this is 2 carbon, this is 3 carbon, and this is 4 carbon. So all the possible structures you can see here. Another something unusual type of reaction it is, but it is also example of Wurtz reaction. See, here both the halogens, they are part of the same molecule. It is not that we have taken two individual haloalkanes. In the last reactions, you have seen two individual haloalkane we have taken, but now it is present in the same molecule. So what will happen if you consider the sodium metal here? So it will be attached with one Br, another Cl. So 2 sodium required, and this carbon and this carbon, these two will be now joined, and now you are getting this type of structure. Two types of byproduct, one is NaBr, another one is NaCl. Here also we are using ether. So when see it is simply mentioned ether, it is basically by default diethyl ether, that is ETOET. Mostly we should call it diethyl ether, but you will see it is simply mentioned ether. So when nothing specific is mentioned, you can consider it as if it is diethyl ether. But here it is mentioned dioxane, but dioxane is also a kind of ether. So for Wurtz reaction, basically ether is used, and dioxane is this type of ether which is cyclic. So here if it is 1,4-dioxane because positions of oxygen 1,4. Mostly if it is nothing is mentioned 1,4 or 1,2, you can consider it as if it is 1,4 because that is the most common dioxane which is used. So this is example of Wurtz reaction where same molecule is containing both the halogen. Now apart from sodium, you can also use metals like silver, indium, activated copper, zinc, and even iron. So it is not limited to only sodium, though that is the most common, but other type of metals also you can use. So if you are seeing any examples like this, don't think that sodium is not there, so it cannot be the example of Wurtz. No, that is not the case. It can be the example of Wurtz. So you have to check whether there is proper positioning of the halogens. Here you can see 4 halogens are attached to same molecule, and you are using 2 metals, 2 sodium, zinc metal, not sodium. So here what will happen? 2 times Wurtz reaction possible. So the first reaction when these 2 carbons will be joined, and the second possibility the other 2 carbons will be joined. So finally you are getting this type of structure. These 2 bonds are the newly formed CC bond. Now after finishing the third reaction, which is reaction with metal, the last type of reaction that is possible for haloalkanes is reduction reaction. So obviously we need some reducing agent. Haloalkanes are reduced to alkanes. So here initial starting material you have started with haloalkane, you are using some reducing agent, and finally what you are getting, final product is alkane. And what is the nature of reducing agent? By treating it with hydrogen in the presence of metal catalyst like nickel, palladium, etc. Or you can also use hydrogen iodide in the presence of red phosphorus. So these are the reducing agent combination that you can use. So here we have taken bromoethane or ethyl bromide in presence of hydrogen. Any of this metal you can use, mostly nickel, palladium, platinum, that is transition metals are used for catalyst, and you are getting this Br is now replaced with H, and another byproduct that will be HBr. Second example, now we have not used, it is not we are using any hydrogen or metal. Now we are using another reducing agent, which is hydrogen iodide in presence of red phosphorus. We know there are different types of phosphorus, red phosphorus, white phosphorus, and here we have specifically taken red phosphorus, not white. So now also we are getting same type of reaction, but here the nature of product is different. Here these two iodine together, it is making the byproduct IO2, and the H that is now taking the position of I. So this question, it is related to Wood's reaction that we have just discussed in the previous slide. It is asking that which of the following reaction is the least effective method for the preparation of methyl cyclohexane. Now methyl cyclohexane, what is the structure? Obviously cyclohexane is there, and there is at any position there will be a methyl. So you are trying to make this molecule, but the question is, out of these four reactions, which one will be the least effective method? That is, which method will not give you better result? So here suppose this is number 1 reaction, this is number 2, number 3, number 4. So the first 3 reaction, that is 1, 2 and 3, both the halogens, they are part of the same molecule. So this will be intramolecular. But for the last one, here we are using 2 different sorts of halide. This is chlorine attached to cyclohexane and chlorine attached to methyl. So this is the, it is not example of intramolecular, but conditions are same. Sodium ether heat that you can see in all these options. Now the first reaction, C, here the carbon with which halogen is attached, this is 1 degree, this is also 1 degree. In option 2 also, this is 1 degree carbon, 1 degree carbon. So when it is 1 degree, the Wood's reaction that can take place very easily. And also in the last example, see, mostly the examples that you will see under Wood's, it is mostly 1 degree. Though there is, in this slide, there is also example of 2 degree, but mostly it is 1 degree, right? So when it is on 1 degree, Wood's reaction will be favored. Because if it is 2 degree or 3 degree, there is a chance of other type of reaction. Fine. So these two are 1 degree. So there is no such problem with 1 and 2. And also these two are intramolecular, and obviously when it is intramolecular, these two chlorine, they can come close to each other very quickly, and reaction can take place very quickly, because ultimately there should be bond formation between these two carbon. Then only you can get cyclohexane ring, because see, 1, 2, 3, 4, 5, 6, total number of carbon is 6. That means when 1 and 6 will be joined, you will be getting cyclohexane 3, 4, 5, 6. And see, at 2 position there is also methyl group. But this is the structure that you are trying to make, methyl cyclohexane. So here it is possible. With option 1 also it is possible. So here, as both the chlorine, they are part of the same molecule, so they can come close to each other very easily. Reaction will also take place very easily. And that is also the case with option 3. But in option 3, though it is intramolecular and both the halogens are part of the same molecule, but the problem is here, 6 carbon, that is 1 degree, but the carbon which is number 1, that is not 1 degree because it is attached to 2 more carbons. So this is 2 degree. So compared to 1 and 2, in this case, Wood's reaction will happen, but this is not very good method. 1 and 2 better than 3. But we have to choose only one option. It is a single correct choice. Okay. And in the last case, now this is not intramolecular. So these two molecules, they are individual, they have to come close to each other, then only reaction is possible. And here another problem is, this is 1 degree fine, but this is also 2 degree. But in 3 and 4 options, in both cases, 1 carbon is 2 degree, that is common point. But the better case is 3 compared to 4, because in 3, it is intra. only in option 4. This is not only having 1-2 degree carbon, but this is also inter, not intra. So that is why these two will be, the last one will be the least effective method. So we can use only primary alkyl halide in Wurtz reaction. If you are using secondary or tertiary alkyl halide, there is a chance of getting elimination. So that is why 1 and 2, these two will give you best result. But among 3 and 4, you have to choose only one. Now among 3 and 4, in both cases 2 degree present. But the problem with 4 is that it is not only having 2 degree but carbon, but also it is inter. So that is why this will be the least effective method for Wurtz reaction. Option 4, that will be the correct option. Which of the following will form Grignard reagent with magnesium and dry ether? So we know that when you are treating any alkyl halide with magnesium and dry ether, you are getting RMgX. So carbon metal bond formation is there. So in these 4 options, in all these molecules, there are not only one halogen but 2 halogens, right? So you may think that in both cases there will be formation of CMGBr 2 times. But actually, if 2 times the reaction is occurring, there must be, you have to give some time. But if suppose the first carbon bromine, it is already converted to CMGBr, but before the other one is also converted to CMGBr, suppose in between this time, if some other reaction is occurring, obviously Grignard reagent formation is not possible. So what happens? For the first molecule, when one CBr is already converted to CMGBr, but the other one, it is still CBr. Under this condition, this type of elimination reaction, see, CMG bond is broken, CC double bond formed, Br is removed. So here the byproduct will be MgBr2, which is stable. So this type of elimination is occurring just before you, that is another CBr is not converted to CMGBr, before that it is occurring. So here you cannot make Grignard reagent. Option A is not possible. So the question is asking which of the following will form. So this will not form. This is not correct. Then option B, here also the position of 2 bromine, 1 and 3 position. And when one CBr is already converted to MgBr, then what will happen? This carbon, now it will have some del negative charge and it will attack this other carbon as if it is alkyl halide. This part is alkyl halide. Br is removed, you are getting cyclopropane ring. So here also Grignard reagent formation not possible. Problem with option C is that now one CBr is converted to MgBr, but now this is also in ideal position for some elimination reaction. So this type of elimination is possible here. Though in this structure it should not be shown. First you convert this structure to the other resonance structure, then you can consider this type of elimination. You are getting CC double bond, and this is known as benzene. Though it is not very stable, but still there is a chance of this type of reaction. So C is also not correct. But this type of reaction is not possible with option D molecule. So when it is converted to, that is one CBr is converted to MgBr, elimination is not possible in the aromatic ring, because for elimination the 2 bromine must be at 1 and 2 position, and also the bond between these 2 carbon like this, that is also not possible. So here you can make a Grignard reagent. Okay, so this will be the correct option, that is option D is the correct option. Identify structure of product. So this question, the second question, you can find some similarity with the previous one. Okay, here also you have started with 2 halogen in the same molecule. They are at 1 and 2 position, so they are at ideal position for elimination, right? You are treating it with Mg and THF. THF is tetrahydrofuran, which is The solvent which is used, it is cyclic ether. This is a very good solvent. Here it is simply mentioned ether, but here it is mentioned THF. But THF is also ether, another kind of ether. It is solvent here. So the reaction that will be here, one CBr will be converted to CmGbr, and this type of elimination reaction is possible. The byproduct is MgBr, and you are getting CC double. So this is the structure of the product, right? Now this is also formed, that is option A molecule. This one, this is also formed, but this is not the end product. You have to identify the structure of the end product, not the intermediate. So A is also formed, but A is not correct option, and C is obviously not correct because the other CBr, even it is that is before converted to CmGbr, just before that elimination like this will take, and option D, this is not possible at all. Okay, so correct option is option B. So now we have finished the chemical properties of haloalkane. Next there will be chemical properties for haloarenes. That means here we will discuss those molecules where halogen, that is directly attached to aromatic ring. So this is haloarene. Now in case of haloalkanes, we have seen 4 types of reaction possible: nucleophilic substitution, elimination, reaction with metal, and the number 4, reduction. But in this case we will see there are mainly 3 types. So reaction with metals and nucleophilic substitution, these two again you can see here, which you have already seen in case of haloalkanes, but reduction, that is not present here, and you are seeing a new kind of reaction which is electrophilic substitution. Now this number 2, that is the most important. The first one and the last one, these are not very important. Okay, even if the last one is important, but nucleophilic substitution, we have also seen this point before while discussing the nucleophilic substitution in case of haloalkanes, that is aliphatic. Then also we have already mentioned that when halogen is directly attached to aromatic ring, nucleophilic substitution is not very, that is common observation. So only under drastic condition or some special cases, this reaction is possible. Otherwise, for haloarenes, that is aromatic halide compound, you will hardly see nucleophilic substitution reaction example. But electrophilic substitution, that is very, very common. Now the question arises here, why electrophilic substitution is so common, but nucleophilic substitution is not so common? So there are some specific reason behind that, and we will see all these points one by one. So nucleophilic substitution reaction for aryl halides, they are very less reactive towards this type of reaction. And this is because of these 4 reasons. So the 4 reasons mentioned here: resonance, then sp2 hybridization of the carbon, because in aromatic ring all the carbons are sp2 hybridized. Instability of the phenyl cation. So when positive charge is directly present on the aromatic ring carbon, that is known as phenyl cation, and this is not very stable. And the last reason is repulsion. But we'll look at all these points individually and elaborately. The first point, that is resonance. In case of haloarenes, we know that the pi electrons that are present in the benzene, they may undergo conjugation. So this is halogen and there is lone pair present. So this lone pair, it can take part in conjugation with the double bonds of benzene ring. That is pi electrons. So now see, there is negative charge here, positive charge here. The next resonance structure, this is the first one. Next resonance structure, third resonance structure. So here negative charge is at 4 position with respect to halogen. In the last one, again the negative charge, it is with respect to halogen, it is ortho. So you can see here, because of this type of resonance, in all these resonance structures, there is CX partial double bond character generated. That is the bond between carbon and halogen, there is some partial double bond character because of this type of conjugation. But this you have not seen in case of aliphatic, because in aliphatic molecule there is no such conjugation possible, right? So it is leading to partial double bond character in the CX bond. Now this partial double bond, when you are treating it with some nucleophile, because we are discussing about nucleophilic substitution. So the reagent is nucleophile, electron rich reagent. So when the nucleophile is in the picture, now it will try to attack this carbon, but breaking of this bond is really difficult, because though it is not exactly double bond, but obviously compared to single bond, pure single bond, now breaking this bond is difficult. So because of this partial double bond, cleavage of this carbon halogen bond, it is very difficult compared to in case of haloalkane, because in haloalkane there is single bond character, no double bond character present. So this is the first reason. So here you can see this picture, which is the average structure of all the resonance structure. So these three resonance structure that you are seeing here, if you combine all these, the average structure that will be like this, where we have used some dotted line because it is not exactly double bond. So we cannot write to solid bond like this. Better you write solid bond and another bond is dotted. Fine. So this is very shorter and stronger. Breaking of this bond not possible or difficult. Second point, sp2 hybridization. So in haloarene, as you can see, this carbon is sp2 hybridized. But in case of haloalkane, this is sp3 hybridized, right? Now, obviously, in case of sp2, here S character is 33.3%, here S character is 25%. So S character is high in case of sp2. Because of stronger S character in sp2 carbon compared to sp3 carbon. That is that we know. So what will happen now? There will be greater capacity for withdrawing effect will be high for sp2 hybridized carbon. So because of this greater capacity of withdrawing the electrons in the CX bond, it will hold the electron tightly. So breaking of this carbon halogen bond, it is difficult, and the bond length will also be shorter because there is some pulling effect. So the bond length in case of aromatic halide and the bond length in case of aliphatic, in the first case the bond length will be less, and when bond length is less, that means it is stronger. It is when it is shorter, obviously it will be stronger. When bond length is high, you can easily break this bond because now bond strength is less. So that is the another reason for which nucleophilic substitution that is not so common in case of haloarenes. Okay, so we will not be able to complete the other 2 points. So that will finish in the next class. Today we are ending here. So next 2 points we'll discuss in the next class. Thank you for listening.
This conference will now be recorded.